let's just do the opposite. I have a cycloheptane, so I'm going to have a ring with how many carbons around it? 7, right? Heptane is going to be 7. On the number 1 carbon, I'm going to have 2 methyl groups. And on the number 2 carbon, I'm going to have a chloro. If I draw that real quick, I can see that now, but why didn't I call this 1-chloro 2,2-dimethyl? Okay? When you're drawing ring systems, you want to you start naming your nomenclature system with that carbon which has the most substitution on it. So on this carbon right here, I have 2 substituents. On this carbon, I only have 1. Even though chlorine comes before methyl in the alphabet, the first rule is the most substituted carbon in a ring gets to be called number 1, and then you name everything after that to get you the lowest number. So in this case, I have 1,1-dimethyl, because that's the most substituted carbon in my 7-membered ring. But chlorine comes before M, because the di doesn't count as alphabetical arrangement. So in this case, even if it did, it's D is after C, right? So this is 2-chloro 1,1-dimethyl cycloheptane. Okay? S-butyl bromide. That's a common name, right? I'm naming this as if it's an alkyl halide. Could you guys do that too? How many carbons in sec-butyl? 4, right? Butyl, butane, sec-butyl. Sec implies that my bromine has to be attached to that second carbon. Okay? I have to know actually what the structure of sec-butyl is. And so I'm going to call it sec-butyl bromide. I'm actually going to draw here S-butyl here and draw a bromine off of it, because my bromine is actually at the secondary position here. That's all that's meaning. Okay? Yes?
Why is there a hyphen in between butyl and bromide?
There wouldn't have to be. That's a good catch too. Sometimes if you look at when you're naming these as alkyl halides, normally you wouldn't have a hyphen in there. I'd probably leave that out too. That would probably be the best answer to have.
So the S tells us that it's on the second carbon?
It's sec-butyl. If I had sec-butyl as a substituent, this would be that big long squiggly line that looked like the parent chain there. And that's why it's sec-butyl, because it's on the second carbon. Okay? Not if you, yeah, you could have named this 2-bromo-butane, right? That would have been the IUPAC system. The common name is sec-butyl bromide. You probably could have called it 2-butyl. It doesn't make sense because we were just calling them alkyl halides. The numbering system never comes into these small molecules when you're using the common alkyl halide names. Yes?
So it doesn't ask us for the common one. We could have named that the 2-bromide.
1, 2, 3, 4.
We could have named it 2-bromo
Butane, yeah,
right?
absolutely.
Okay.
Same compound. Let me escape here. Oh, I don't have the program for drawing here. I'll have to fix that one right there. Let me go back up there. How about this one? Okay. You can see here, I still have butane. I have an iodo at the 3rd carbon. I have a chlorine at the 2nd carbon. Okay. C comes before L, therefore my chlorine is at the lowest number here. But I'm also implying, I'm not just implying, I'm telling you, there's stereochemistry involved, right? And so we're going to have to use dashes and wedges. How are we going to do that? Well, typically what I would do is I would draw out the base structure first and then look at each one. I'd look at this one and say, well, I've drawn it as if it's going into the plane here. Let's just check it and make sure it is actually the R enantiomer. So if I, or at
Wouldn't
least
it be
that's,
the S because you named it as 2-chloro?
so 2-chloro is 2R.
So then
So, but you're pointing at the.
I'm looking at chloro. Thank you. 1, 2, so 2 chloral. Let's just check this one to make sure it's right, okay? So I have 1 priority, 2 priorities, 3 priority, my hydrogen's in the back of the board, so it is actually gonna be R. That's right then, right? Okay. If I look at the iota one on the carbon number 1, 2, 3, I go first, second, third, that's clockwise, but my hydrogen is sticking out at me, so it's actually gonna be the S. That's gonna be the 3S for that chiral carbon. What would be the stereochemistry of, what would I call its enantiomer? The non-superimposable mirror image. What would it be? 2S, 3R, right? It's just going to be the opposite of that. I have to switch all of them to come up with the enantiomer, the non-superimposable mirror image. I have 2 chiral carbons. I have to switch the orientation of both of them.
Can you go over the word iodo, please?
Iodo? Iodine.
Iodine, but.
Iodine. It's just like chlorine.
Oh, okay,
Iodine, we just go iodo.
okay. Oh, I was going with the iodil, that's what I was doing.
Oh, iodil, yes.
Quick question. So what would make the carbon that has the chlorine on it have higher priority for being the number 2 carbon versus the one with
Alphabet.
iodine?
Alphabet.
Just the alphabet?
That's alphabet when we're talking about halogens. That's the only reason. It becomes, because this I could go 1, 2. I could go 1, 2. C comes before I. That's all it is.
Okay.
Yep.
And is that the only difference that makes that one like a more important carbon than
Yep.
the other one?
Yep. Having said that, what if I had the chlorine out here? Then I'm going to have the lowest numbering on that first one, so you could call it 1 chloral because you hit that substituent first, right? But in this case, we hit it both at 2. Okay? Okay?
So when we draw its mirror image, how do we deal with the stereochemistry again when we draw it?
Put that one out,
Okay,
put that one in.
that's it.
That is the enantiomer,
Okay.
the non-superimposable mirror image. Okay? Because if I draw this one out of the board, that implies the hydrogen is back in the board, right? So you literally just then need, that'll make that the R1. If I change the stereochemistry of any 2 groups at this chiral carbon, if I put the chlorine back into the board, that's going to be the 2S then.
Okay.
Yep. Yes, you do space, yeah. So it's an alkyl halide, and there's a space in there. But I need to have ChemDraw in here to modify it. I drew all these in ChemDraw, which is a program that allows you to draw molecules, and it's not on this computer. It's back in my computer. Extra point for catching that mistake. Go ahead.
So just to double check for the whole iodine chlorine thing. So
Yep.
then for the numbering, it doesn't matter what their atomic number is
Nope.
for priority for
Nope.
the halogens?
Well, for naming them, okay. If you were looking at R and S, we typically look at their atomic number for ordering them for R and S designation, right?
Mhm.
So bromine, if I had a bromine and a chlorine on the same carbon, bromine would have the higher priority for the Ingold-Kahn Krylov nomenclature rules, right? For R and S. Any other questions? Okay, let's look at some property trends, just of these alkyl halides. What is the electronegativity trend for halogens? Okay, which one is the most electronegative? Fluorine. It's actually the most electronegative molecule on the periodic table. Right? Okay. So, and if I put some numbers to that, this turns out that happens to be 4. That happens to be the largest number. That has ramifications for its dipole moment, which we're going to talk about just in a second here. Because the more electronegative, it's pulling electrons toward it, right? So it's going to be charge separation, which gives you a dipole moment. Also, included in a dipole moment is how long that bond is. How about this case? Which ones have the shortest bonds and which ones have the longest bonds? Is the smallest or the longest bond? Smallest, right? Because it's just a little teeny fluorine, okay? There's not as much electron cloud there. So I have a very small separation between a carbon and a fluorine, okay? You combine those all together, we can actually do some mathematics to get our dipole moments, but let's see if we can do it intuitively, because I need to know the charge separation, and I know need to do the absolute charges. The electronegativity tells us a little bit about the charge that's on the fluorine compared to the carbon. This tells us how far they're separated. If I do the multiplication with a few little factors into that, it turns out which one's going to have the largest dipole moments. Most of the influence comes from electronegativity. So in theory, I'd say, well, maybe it's carbon fluorine has the largest dipole moment, but it's